Thank you very much for coming to this talk today. This talk is going to be all around Gateway API, which is a new project that's up and coming, part of the Kubernetes project. And we're going to talk about Kubernetes networking and how Gateway API is going to apply to Kubernetes networking, but also how it's going to apply to on-prem and the edge and things like that. So my name is Dan Finneran. I'm a community technical advocate at Isovalent. We focus on the open source upstream project Cilium, which is one of the CNIs for Kubernetes, and quite a bit of reverb. It's all based upon eBPF, which provides a lot of its underlying functionality. So this is the agenda. You're kind of quickly kind of go through why I put this talk together. We'll do a bit of an overview of Kubernetes networking, because for those that haven't really delved into it, there's a lot of kind of moving pieces, and it's good to understand those moving pieces to look at how they're actually going to change when Gateway API matures to the point that it's hopefully going to get to. Gateway API, as I mentioned, it's a relatively new project. We're going to go into what Gateway API is, its constituent parts, and how your applications are going to be defined using Gateway API. And then from an edge and on-prem perspective, we're going to look at how Kubernetes interacts with physical networks. We'll do a quick demo, we'll wrap things up, and hopefully there'll be time if anybody has any questions for me to answer them. So, why this talk? So, Kubernetes is becoming kind of the de facto for landing applications. A lot of new applications have been developed to run on Kubernetes for quite some time now. There are a lot more existing applications making their way onto Kubernetes, and existing applications come with a lot more requirements on existing network infrastructure and things like that. Out of the box, Kubernetes doesn't do any networking. So if you've been born in the cloud and you've basically deployed things with EKS and things like that, networking has always worked. If you have your own set of servers in your on-prem environments, you'll deploy Kubernetes, and at which point you realize most of it is actually missing. So there are a lot of additional bits that you'll need to put on there in order for Kubernetes to actually do some networking itself. And the networking is evolving. So originally, the constituent parts you'd add into a Kubernetes cluster to do that networking were largely just focused on allowing pod-to-pod traffic, getting traffic through the Kubernetes cluster to the outside world. They're doing a lot more things these days. They're doing kind of IPAM to the outside world. They're bridging from inside the Kubernetes cluster to the outside world. So we're now having to focus a lot more on connecting your internal Kubernetes networking to the external world. So bridging from the logical inside a Kubernetes cluster to the physical network world. So as I said, this is kind of why, the reason for this talk is because this is becoming a bit of a problem, but there are solutions that are being put together. We're moving those existing applications, those legacy applications that need to connect to existing things outside the Kubernetes clusters, and we need to kind of come up with ways for doing that sort of thing. So, to kind of kick things off, we're going to step through what Kubernetes networking actually looks like under the covers. So, to kick things off, obviously, back in the day, you had computers and applications. So I would have a server. My server would have an address on the network. I would run my program, my application on my server, and I would just connect to it. I would connect to the IP address of that server on the port that my application was listening to. Didn't really need to care about anything else. That was it. It was very simple, one-to-one, very simple, very straightforward. Then containers kind of came along. So I would have my server that would run my application in a container. So typically back then it was, well, still is kind of Docker. I would basically create a Docker container. Docker networking would give me an internal IP address inside the server itself. I would run my program in there, but I don't connect to my container directly. I can't access this IP address from the outside world. I can only access the IP address of the server itself. So what we typically would do is we would map a port from the container itself to the IP address of the server itself, and that is how you traverse from the outside world into the server, into the container that's actually running on there. So that's a quick kind of how you would, how the networking typically looks from a container perspective. That's pretty simple, that's pretty straightforward. internal network, running my container, running my application, and I need a way from bridging from the outside world internally to that. So what is a Kubernetes cluster? What does that look like from a networking perspective? Messy from an outward world perspective. We have many servers, many worker nodes that are making up a Kubernetes cluster. I have then many pods that are running on my many nodes that all have those internal IP addresses that I can't access directly. So this is typically what your cluster would look like. You have all of these nodes all running many pods. You have all of this internal networking that you need a way to kind of traverse in order to get to those applications that are running inside those worker nodes. So what does that actually look like? So if we drill down, we have our single worker node here, worker node 01. I have my one pod that's actually running on here, and I have the IP address to the outside world. And then I have my kernel, which is effectively the logic that is actually running inside my machine itself. So in order to get traffic into my application running on a Kubernetes cluster, we have the concept of a service. So I have two nodes here. Both of them have IP addresses that are accessible on the outside world. Then I have two pods that are running inside the cluster. I can't access those directly. We create a service. The service binds all of the pods that I care about. So we basically say I want a service that will expose these pods based upon labels and selectors. That will give me another internal IP address. So that is the service IP address that we can see here. I still can't access that externally. But if I can access that inside the cluster. If I go to that 10.96 address, it will go to one of those pods that sits underneath the service. I still need a way of getting traffic into that, and the most basic way of doing that, if my slide builds out, is the concept of a node port. So these are Kubernetes objects. These are the most basic ways of getting traffic into a Kubernetes cluster. If I add a node port to my service, simply what that does is that will configure the kernel logic on all of the nodes in the cluster to suddenly start exposing that node port. If I access that node port, then I will access the service, and then I will access one of the pods that sits underneath that service. So we're starting to build out like the full end-to-end connectivity to those pods. And as I mentioned, the node port is the most simplest way of exposing applications that are running within your Kubernetes cluster. So, as I mentioned, the node port is the most simplest way. It's not great in that you basically would, from an outward perspective, you need to find one of the nodes that you want to connect to. If you set up configuration to one of those nodes and that node goes away, then all of a sudden your end-to-end connectivity doesn't work and things like that. So the nicer way of doing that is through a load balancer type service. So what does that kind of look like? So again, we have our worker, we have our pod, we've created a service that will access one of the pods that it cares about. A load balancer will give us a new external IP address. It will configure all of the kernel logic, so any of the nodes that see traffic coming in on our load balancer address, it knows about and knows to send it to the service. The service then knows to send it to the pod underneath. So, as I mentioned, traffic that goes to that load balancer IP address will go to one of the nodes where that load balancer IP address is hosted, onto the service, onto the pod itself. So, a few observations. As I mentioned, we have an external load balancer. Where does the external load balancer come from? Who's doing that? So on an on-prem environment, there are a number of projects that will take care of doing that for you. Cilium, MetalLB, for example. Or you can invest in things like F5 load balancers. In cloud-like environments, again, it's just magic. You basically will create a service, expose it as a load balancer, and pay some money, and a magic external IP address will come into play. But as I mentioned, we're kind of focusing here on kind of edge and kind of on-premises environments. Who's giving us those IP addresses? Well, somebody needs to be in charge of, kind of being aware of the local configuration for that. And when we do get one of those IP addresses, how do we expose that to the network? How do we update the physical network? We need to have, technologies in order to do that sort of thing. So, there is a component inside Kubernetes that kind of manages a lot of that magic. If you are running a Kubernetes cluster in the cloud, AWS, etc., the cloud controller manager performs the magic. It is the bridge between your Kubernetes cluster and the infrastructure in which it lives. So in cloud environments, the CCM will speak AWS APIs in order to get you your load balancer. Once it's got that IP address, it will update the Kubernetes cluster, which will update that kernel logic, and then you have all of that end-to-end logic all plumbed in. Traffic that comes in through that load balancer, the Kubernetes cluster knows about, goes to the service, goes to the pods, and things like that. Again, on-prem, those APIs don't exist. We need to have that logic that comes from somewhere. So a quick kind of Kubernetes networking recap. The pod, a pod is one or more containers, and it is given an internal IP address. We can't access those, or you shouldn't access those directly. The service creates a new internal IP address, which sits on top of all of those pods. So if I hit that service, I'll hit one of those pods that sits underneath it. Typically, we don't access the services directly either. To get traffic into a service, we have node ports, load balancers, and a few other objects which will bridge from the external world into the cluster, onto the service, onto one of the pods. But again, something needs to connect that cluster to the underlying infrastructure. As I mentioned, in the cloud, all of that magic happens itself. On-prem and in the edge, we need to code logic in order to bridge those gaps. So that's a very quick recap in terms of Kubernetes networking, services, load balancers, etc. There are only kind of a few objects that exist today inside Kubernetes that will allow you to do networking. The Gateway API project is a new project that is going to expand a lot of all that and break it down into a number of constituent parts which will enable us a lot more functionality. So why has this Gateway API project kind of come into life? Why are people working on it? As I mentioned, there's only a few objects that exist in order to do networking inside Kubernetes today. And the current design kind of blurs a lot of the lines of responsibility. So as an application owner, I deploy my replica set or deployment, whatever. And then I create a service of type load balancer. All of a sudden, that one person's line of responsibility has gone from the application to the networking to everything. We want ways of kind of breaking things down. It's kind of almost amusing, at least to me, in that many moons ago it was all about breaking down the silos so that one person could kind of do everything. Now we've gone kind of back to a certain degree where we're putting up not silos, but kind of clearer lines of responsibility in terms of who should kind of be doing what. And also, there is issues to a certain degree in that some of the high-level abstractions, things like ingress, for instance, each of the different providers of ingress logic have done it in their own kind of unique way. So if you have your application all defined with all of these different layers and you want to change from one implementation to another, you can't just change kind of like the type or the API version or whatever. You typically have to re-engineer your ingress to this different provider. So standardization is, So what does Gateway API hope to provide? Standardization. So it's a standardization of how applications are expressed within Kubernetes. So we start to break things down into smaller components. Clearer separation of responsibilities. So certain teams can take care of some of the lower level networking and then leave the application people to focus on what it is that they really hope to achieve. It becomes a lot more simple for people who are creating the Gateway API components to express what it is that they want to do. And then a clearer hierarchical design, so it becomes quite clear when looking at it what the constituent parts are actually doing. So let's look at the new architecture. So I went through the previous architecture of pods and services and things like that. The Gateway API architecture, as I mentioned, is made from a few more parts than that. So here's my infrastructure. I have 3 pods that make up my application. I've put a service on top of all of those. Oh, this is a quick recap, sorry. And then I use a load balancer to expose it to the outside world. So anyway, right, so Gateway API. So the first constituent part is the Gateway API class. With some of the other objects inside Kubernetes, class typically is used to define pretty much a vendor implementation. So this Gateway API class could be the gateway API class AWS, it could be the gateway API class Cilium, it could be the gateway API class Dan's load balancer, for instance. That is my implementation, or that is an implementation of gateway API. And then inside gateway class, we have the gateways. Now, here I've defined 3 gateways that are going to exist inside this particular cluster. So we've got one for production, one for testing, and one for internal services. And those gateways effectively are IP addresses. So they could be internal, they're more than likely going to be external IP addresses, which are gateways into the Kubernetes cluster itself. So those are the first 2 constituent parts. You have the class, which defines the implementation, and then you have the gateways, which are the entry points into the Kubernetes cluster itself. Simple, but how does that actually relate to getting traffic into the Kubernetes cluster itself? So the concept of routes inside a gateway API implementation are the way into the actual cluster itself. And that is the mapping between the outside world and what's actually coming into the cluster itself. So there's a number of obvious kind of routes that exist in the Gateway API project. The most common is the HTTP route. Gateway API's initial implementation is largely focused on kind of clearing up the ingress mess, which has kind of occurred naturally through kind of the evolution and stuff. So the HTTP route is the most obvious route of the Gateway API routes. It is effectively in charge of managing incoming HTTP traffic. It's layer 7 focus, so it will look up the route that you've actually had in there, and then we'll send traffic to where is defined as a backend on that route itself. And then additionally, TLS routes, so ensuring that traffic is encrypted as it's coming in. TCP routes, so TCP ports mapped to a gateway, mapped to a service. UDP routes, gRPC routes, etc. These are the basic routes that are defined in the Gateway API project itself. However, the options are kind of limitless for the sorts of routes that you could look at implementing. Some of the telcos that I've been working with are looking at kind of a mirror route, for instance, where traffic comes in, it goes to a service, but the traffic is also mirrored to a detection device or things like that. As I say, the options are kind of limitless, but the routes are effectively what happens as traffic kind of enters the cluster on a certain ingress point. So let's kind of finish building this out. We have my gateway class of a certain implementation. We have our 3 gateways, which are the IP addresses. Now we can start to attach those routes to our gateways. So we can see in production, we've got a HTTP route, which is going to map to /login on that IP address. That will go to a set of pods that will handle the HTTP traffic for login. Our testing, we have some simple web traffic listening, sitting on port 80. And then in the backend services, we have UDP routes pointing to probably DNS servers, and some more web services are exposing themselves on the admin path and things like that. So routes bind to gateways, and gateways live in a gateway class. That's effectively the architecture of Gateway API. And you can start to see that it kind of separates things a little bit more than we just had before. We basically just had services. And that was it. Services pointed to something. Now we can effectively leave the application teams to basically just add the routes that they need to care about. And then other teams can take care of, the networking teams could take care of caring about the gateways that map in the infrastructure and things like that. So a quick Gateway API recap. As I mentioned, the gateway class defines the implementation of a particular gateway API from a vendor or a project. A gateway is a networking endpoint in the cluster that typically would be provided by infrastructure teams or networking teams. And then the varying routes, they're the ingress routes typically into the Kubernetes cluster. So they define the types, the protocols, and the behavior of the traffic as it comes in on that particular route into the cluster. So what does it look like at the moment? So as of a couple of weeks ago, Gateway API is version 0.8, and version 1 is scheduled to come out for the next KubeCon, which is in a couple of months' time. So there's a lot of work that's actually going on at the moment. The main focus of the Gateway API project to get to version 1 is largely on the ingress side of things at the moment. So a lot of work is basically being done with ingress controller teams and the Nginx group and Cilium and a bunch of others are largely all focused on kind of the ingress side of things. The TCP routes, UDP routes, gRPC, and TLS, a lot of the implementations support those today, but they're still in alpha, and they will be going to beta once we reach V1 and things like that as well. From a Cilium perspective, so Cilium is a maintainer of the Gateway API project. We have a number of the engineering team focused on kind of developing on that. The Gateway class and the Gateway objects are first-class citizens in there, and from an on-prem perspective, I'll kind of go into what that actually looks like in a second. The HTTP routes all kind of map directly to the service mesh side of things, so it programs the underlying envoy and things like that. And TCP routes and UDP routes, which are effectively going to start to replace the load balancers that we've been kind of using for quite some time now. Those are going to be added in kind of upcoming releases shortly. And as I've mentioned, there are a number of routes that are part of the Gateway API project, but the ideas are kind of pretty limitless. As I mentioned, the mirroring routes, the inspection routes and things like that, there is no end to what we could actually implement as a route that defines and actually maps to what end users are actually trying to do as part of the Gateway API project. So I've kind of quickly gone through what networking looks like today, what Gateway API is going to bring to networking. The big question really, though, is how this interacts with physical networks. So where do these IP addresses come from? How do we update the network? What are the technologies that are required in order to do those sorts of things? So Gateway API to an IP address, for instance. We have our implementation. We've defined a gateway, which is production. That needs an IP address in the infrastructure that it's running in order for traffic to actually traverse the network to actually get to it. So this is typically the constituent parts of Gateway API. The code that somebody needs to write will live in a controller, so you'll have a number of controllers that will make up your Gateway API implementation. The Gateway controller is typically going to be in charge of speaking to the network, understanding the network, and configuring things so that this Gateway object understands the network and can be present on there. So we've defined our gateway. The Gateway controller now needs to do some logic in order to finish the configuration of that gateway. What it's going to need to do is do some sort of IPAM in an on-prem network. We need to understand the configuration of that network. We can't just pluck an IP address out of thin air. It needs to sit from a range or things like that. So if you're writing your own, you could write your own IPAM if you want to do such things. I don't recommend it. I have done it in the past, and it's not fun. Typically, you can make use of existing vendors. So Cilium manages its own IPAM. Additionally, though, so Cilium can manage its IPAM. You can give set ranges to Cilium. It will take care of choosing an IP address from that range which fits with the network. It will take care of the life cycle of that. It will give that IP address back to the Gateway controller, which will then program the object inside the Kubernetes cluster, at which point your gateway is configured with an IP address that makes sense in the infrastructure. You could, however, programmatically use tools like Netbox, which is a big IPAM project for understanding various networks. So your gateway controller could sit and speak to the Netbox, get an IP address, and program it in the same way. So from an on-prem perspective, there are a number of different options that do exist in order to get and understand those physical networks. Cilium out of the box, you can basically give it those ranges of the network that it's living in. It will take care of doing all that sort of stuff for you. Other gateway controllers will speak to Netbox or have their own IPAM implementations in order to do that sort of configuration. So something understands the network, something has given us that IP address. We now can bind our routes to that gateway. So we've added in a TCP route, which will point to a backend service. That route is port 443. We have our TCP route controller now, and that will need to do some additional logic. So what will that do? On an on-prem perspective, that will configure our service to use the gateway IP address, attach that to the load balancer side of the service, So that now the logic in the Kubernetes cluster, the kube proxy has been updated, so it knows that traffic that comes in on that load balancer IP address, so traffic that comes on our gateway side of things, that hits this particular port, we understand, we send it to the service, which will send it to the pods that sit underneath. Dependent on your implementation, it could well be that you have a different data plane, so the TCP route may have to speak eBPF, and it may have to configure kernel logic underneath, or it may just configure kube proxy and things like that. Currently, it needs to configure the services, and it needs to configure the load balancer side of things. In the future, it is expected the Gateway API could actually remove the concept of services. So that object that has been part of Kubernetes now for 6-7 years may go away, and it may just be Gateway API that is the sole implementation for how you architect your applications and networking inside a Kubernetes cluster. So that's kind of the end-to-end logic, but none of that actually says how it's actually going to make any changes on the physical network itself. So whilst we can do all of this logically, we need technologies that are going to bridge the logic of a Kubernetes cluster to the outside world. And typically on-prem or in an edge environment, there are kind of two main methods for doing that. So the first and most simplest is a technology called ARP, so Address Resolution Protocol. Typically, we're all using ARP all day, every day, without really realizing it. When you came in here and connected your phone to the Wi-Fi network, there was an ARP broadcast which basically said, my phone is on this network and has this IP address. So ARP typically is a table that all devices on the network have, which basically says, here is a physical address, so the hardware address of the device, and here is the IP address of it. What that typically means is that when I need to send traffic from one IP address to another, I need to know the hardware of where it's going, because I need to send a frame to where that's actually going. So we need this because we need to update where IP addresses are inside a Kubernetes cluster. If I define a gateway and I get a new IP address, that needs to be present on one of the machines in the Kubernetes cluster. And I need to tell the network where to send traffic to so that it can go to that IP address, so it can go to that machine, so it can make its way into the service, so it can make its way to the pod that sits underneath. So whenever a gateway is created with a new IP address, using IPAM, I will send a gratuitous ARP, which is basically everybody. This is the new IP address, and this is the hardware that it's sitting on. And now all machines in this network know where to send traffic to, which physical device to send traffic to in order to get it to that IP address. And that is the simplest way of updating a network with updated IP address to hardware location. So we can see here I've got my load balancer that's running on the node here. I've got a new external IP address that is mapped to my first worker. I have done a gratuitous ARP, so we now know that on the network, I send my logical frames to this hardware address, because that is where this IP address is actually living. In the event that that machine dies, the network connection fails or whatever, the logic of Gateway API will re-plumb that IP address to one of the other machines that sits in the cluster. So this IP address will now be attached to this interface. I send a new gratuitous ARP update, everybody updates their tables, and my packets will make their way to the new machine that has that IP address in the cluster. So that's very simple. That's basically how most of it actually kind of works from a layer 2 ARP perspective. Now, that's fine. In edge environments, that's the predominant deployment methodology for how you're going to do these sorts of things. In larger data centers or much larger scales, you're going to work in a slightly different way. And in most cases, that's going to be done through BGP. So BGP is a technology that a lot of people don't really ever interact with, but it largely powers everything. It binds the internet together. Whenever new ranges are appeared, BGP basically tells everybody, this is how you get traffic to me. So how does BGP work to ARP? So BGP effectively allows machines, routers, networks, etc., to tell other networks how to get traffic to IP addresses and network ranges. So for instance, we can see here, I have my 3 machines, and they can all actually have the load balancer IP address running on them. So with ARP, only one machine can actually have it at once, otherwise you'd get an IP address conflict. All 3 machines are saying, send traffic to me, you can't do that, because otherwise frames will be broken and it just won't work. With BGP, it's slightly different. All 3 of them can effectively have that IP address. And what they do with BGP is they will speak to some hardware equipment, typically a router or a top-of-rack switch, and they will say to that router, I would like to advertise this gateway address. So when traffic goes to that router now knows that to get to that IP address, I will route it to one of these machines which are saying, I have this IP address. And that's effectively what BGP is doing. It is an announcement protocol which basically says, if you want to get traffic to this particular IP address or this IP address range, send it to me and I will answer, or I will continue routing it to where it needs to go. And that's effectively how you do networking, slightly larger networking on a layer 3 perspective. And in the event that one of the machine dies, that machine will have stopped advertising that IP address. So it's connection-based as well. So as soon as this connection dies, that machine is no longer telling the router or the top-of-rack switch, send traffic to me. The router now knows to stop having that in the routing table, and traffic will continue to nodes 2 and 3. Right, so that's typically how you are updating your networks from a layer 2 or layer 3 perspective in on-prem and edge environments. We're going to run through a quick demo end-to-end of what that will actually look like. So, I don't know if you can see that okay. It does get a bit brighter randomly once it kind of gets going. So effectively, what we have here is we have a Kubernetes cluster, and I have 3 sets of YAML here. I have my gateway class, and my application, and a TCP route. There's nothing running in my cluster at the moment. I've deployed Nginx, as everybody does for a demo. We can now see that I have my 2 pods running. They have those internal IP addresses. I can't access those pods directly, as mentioned, because they're internal to the cluster. And we can see that both of them are running 2 of 2, etc. So the first thing I'm going to do is I'm going to deploy my gateway class, which is my implementation type. What this allows us to do actually is to have multiple implementations of gateways running separately if that was something that somebody would want to do. So we can see here, kind of, at the top, my gateway class is implemented. And what we're going to do now is we're going to deploy a gateway which connects that gateway class. So if we look now at the gateway, we can see here it has been given an external IP address that makes sense on this network. So it's done some IPAM. The gateway's been given an IP address. So we can now think about getting traffic into that cluster itself. And the final thing I've done is deploy a TCP route. That TCP route will expose an external port, and we can see here TCP route's been deployed. We can see on the bottom line it's mapped port 8080. We can also see the IP address from that service matches the gateway. So we now have an end-to-end deployment of gateway API, and we've connected to that IP address on the port defined through the TCP route. So we've done the gateway class, which is the implementation for it. We've done the gateway, which has done IPAM for the network itself. We've deployed the TCP route, which is the TCP port, which maps to the gateway, which maps to a backend service. That will configure the internal Kubernetes logic, and that is the end-to-end deployment of gateway API for kind of an on-prem environment. Oops. So we've gone through the entirety of kind of Kubernetes networking. We've talked about gateway API, how that's going to change that. We've talked about how you update physical networks with these new IP addresses. Kubernetes is continuously evolving, and it's finding itself in a lot more places. Telco is a big driver for a lot of the things that I've talked about today, along with kind of a lot more edge deployments, infrastructure of things, Internet of Things, and things like that. So networking is evolving at quite a rapid pace in order to fit these new demands as we move a lot more kind of older applications that need to connect outside the network and need, to ensure that traffic is stable and things like that, we're going to need to keep evolving Kubernetes networking. Larger teams are sharing Kubernetes clusters, so there is now a more defined need in order to have those clearer sets of responsibilities. And yeah, Kubernetes is just finding itself in more kind of crazy places where it needs to interact with different types of infrastructure, and we need to keep evolving and coming up with new tooling and projects, etc., that can bridge those gaps. So with that, that's the Gateway API project. That's how Kubernetes and Gateway API look in on-prem and edge environments. Thank you very much. And if anybody does have any questions, yeah, thank you. Cool.
Hello. Yeah. Thank you, Dan.
No problem.
Hello. So, very quick question. It appears to me that the Gateway API is kind of like a declarative way of doing ingress for a Kubernetes cluster. Is there any thought of extending that to do networking between Kubernetes clusters as well?
So you certainly could do that. Out of the box, Gateway API is largely focused on external traffic into a single Kubernetes cluster. You could certainly have the concept of a route that would bind to a gateway, which would send traffic to another gateway in a different cluster. Nobody has done that, but the Gateway API project is certainly flexible to have the concept of routes that would do those sorts of things.
Another question?
Obviously, in the demo, there was a TLS route, right, that you configured. You didn't show it, but in terms of, like, if you want to mount, you'll need to mount a certificate into that. What does that look like at the moment for, like, sort of provisioning a certificate for that TLS route? Sure. And is there anything available at the moment for the rotation of those certs, or is that not available at the moment?
So the demo I showed was a TCP route. Not a TLS route.
However,
TLS routes typically will, the demos that I have seen of people implementing that, typically will have implementations of, or will reach back to cert manager or provisioning service of certificates. And they will effectively, the idea is that you create a TLS route, it will take care of provisioning based upon the SAN or the domain name, etc., create those certificates, put them where they need to, and they basically then will go in the data path for traffic that's kind of coming in. All of the routes that I've talked about typically are made by vendors, made by projects, etc. So if you wanted to create your own route that did that sort of thing specifically, then you can do. There's only a few TLS routes that have been created by some of the vendors, and some of them use their own internal logic for doing those sorts of things. Cool.
Hi. I was wondering, how does this and kind of service mesh kind of come together with you've got the mesh gateways.
Yep.
And then this gateway, how are those kind of come together?
Yeah, so, and I know it sounds a little bit crazy on the outset, but effectively this will sit on top of those service meshes. The idea really being is that this kind of standardizes the entire stack. So whilst it does sound crazy to have yet another layer on top, that layer is transferable between different service meshes. So the problem that you kind of have, I think I talked about a little bit earlier, if you define one config and you want to change to another vendor or have multiple vendors running, you may have different teams, multi-tenancy requirements, and they're all wanting their own different vendors of service mesh. That config is not going to transfer east-west, etc. The idea really is standardization. So you'll create your HTTP route, and you'll have the rules in there that define traffic should go to this underneath. With with Gateway API, you can kind of move that to a different provider just by changing the Gateway API class. So yeah, it sits on top of existing service mesh implementations, basically.
Cool. Another question? Okay, I have one.
Oh, sure.
Two, actually.
Oh, wow, okay.
These will be a replacement for all the service mesh, like Istio, Linkerd. That's the first one.
Yep.
And the second one is, this is ready for production?
Good question. So Most of the vendors now have gateway API implementations. So Linkerd, for instance, Cilium, Istio, etc. They all have gateway API implementations. They, at the moment, sit on top or sit next to the current way of defining your ingress config and things like that at the moment. The idea, and this is as gateway API, moves to production readiness for KubeCon Chicago, which is in a few months. That's when V1 will come out. The idea long term in the future is that gateway API will become the de facto way of defining networking in Kubernetes end to end. So as I mentioned, services will eventually, in theory, this is the plan of the project, services could go away, and you basically have pods, and then you basically have gateways and TCP routes that will bind to pods that sit underneath there. Same with ingress configs and things like that. But this is all future vision stuff at the moment.
Thank you.
Cool.
We have time for one question. No?
Oh,
Okay.
oh, 2 questions.
So you talked about BGP.
Yes.
And also there is OSPF. So which one is comparatively better? So
That's a networking question out of my ballpark, really. But I'd say, from what I see, BGP is pretty much the de facto for most kind of deployments, and it's largely what's asked for. Most people that we see typically are using BGP to do kind of route management inside their networks. There are other protocols, but no one is typically asking for things like OSPF or the others that escape my knowledge at this point.
all right, yeah, thank you.
No worries.
Quick question, actually. So in a Cilium cluster mesh setup, we have global services. So do we foresee something similar with gateways, where you could probably like fail between gateways or balance across gateways across clusters?
Yeah, so at the moment, gateway API implementation is per cluster. But there is no reason, and there is some roadmap items effectively where a gateway class with set labels, etc., couldn't span one or multiple clusters, at which point then, yeah, you define a gateway and it will live in one of those clusters. BGP would need to inform the network so traffic goes to the right area in there, or ARP. But wherever that gateway is, as long as the network knows where it is, traffic could go to that gateway and then could go to pods that sit underneath it, regardless of where they are. Cool.
Thank you for coming. Thank you, Daniel.
Thank you very much.